Alright, hello everyone. Let's just fix that. Okay, give me a moment. Okay, hello and good evening. Welcome. Anyone on the stream, welcome. Alright.
Hello.
Hey CJ, how are you?
I'm good. How are you?
Doing good, thanks. Alright, so I want to ask, what are we doing today?
Mechanics. 2.1 and 2.2.
Alright, 2.1 and 2.2. Alright, let's just put that in. Here is the Jamboard, by the way. Let me just share that. Okay. 0.1 and 2.2, that would be kinematic equations and forces, right?
Yes.
All right. So,
Is the friction one
that's
like
2.2.
on a ramp? Is that okay?
That's 2.2, but a special case for 2.2. All right. Um, I think we're gonna
Oh, it's,
go to.
but I got it a lot.
Mm-hmm. Um.
Yes.
All right. Hold on. Let me just update the settings on the stream before we continue. About forces. Okay. Okay. Update all. All right. So let's start. First of all, let's do. Hold on. Okay. So let's go here now. Okay.
Mm-hmm.
Oops. Let me just change settings quick. All right, so when we have 2.1, again, I'll just, this is kinematics. Most of you
Yeah.
would probably know this as SUVAT, right?
Yeah. Suvat.
Okay, SUVAT. And then this would be forces, um, just forces, okay? So, um, let's kind of look at the ramp problem first. So let's start with 2.2, okay?
Mhm.
Uh, all right, so let's take a look at this generalized ramp problem first. So the simplest possible ramp problem is this, and you have your object, and let's say that this object has a mass. Let's give it a value this time straight away. So let's say this is 2.5 kilograms, okay? And that this angle is, let's get an easy angle to work with first, 30 degrees, okay?
Mhm.
Uh, let's also say that the object is in equilibrium, okay? So before we identify the forces here, let us say that the ramp is rough, okay? Now, it's important to note whether ramps are rough or smooth, okay? So I'm going
Right.
to disregard smooth for
Like
now.
snow, or because I had one where it was like a sled.
Mm-hmm. All right.
Yeah.
Now, what does it mean? When we say rough, this means friction is not negligible. Friction is significant. Okay.
Hmm.
Significant friction. And smooth means negligible friction. Okay. So smooth would mean negligible friction. Negligible friction. Okay. So in our case, the ramp is rough and everything else is given. I'm not giving anything else, right? The question now becomes, um, if the let's not put it like that first. Let's just keep it simple for now. What is the frictional force experienced by the block? Okay, so all of your problems, whether whenever you have a ramp problem, all of your problems will look something like this.
It's kind of zoomed in for me. If it could like move to the left a bit, like the
Okay,
screen.
sure. Let's move the screen to the left. Hold on. I'll make that screen a bit smaller. Can you see it now?
Oh, okay.
Can you see it now clearly? Great.
Yes.
Okay. So what is the frictional?
Um, did you write anything on the left side of the triangle?
No, nothing. That's the leftmost thing
Okay,
there.
okay.
Okay. So what's the
Right.
frictional force, right? So the trick here, before we
Yeah.
continue, okay, the trick is always the same as before. Resolve forces along the x and y coordinate directions. Okay. Resolve.
Mhm.
Let me redo that. Resolve forces along the x and y directions. The trick with ramp problems, though, aside from this, okay, the second part of the trick here is, okay, you pick the x-axis to be the surface of the ramp. Okay, and the y-axis is perpendicular to the x-axis still. Perpendicular to the x-axis, i.e. the ramp surface. Okay.
Yes.
Okay. This is one of those few cases wherein you don't just draw a vertical x and y axis immediately. All right. Uh, so let's solve this problem. I'm going to show you how to solve this problem, solving the frictional force given only the mass, the angle, and that the ramp is rough, right? Okay, so there are two ways to approach this. I'm gonna approach this the traditional book way for the beginning. Okay, so approach one,
Mhm.
and this is the one that you would normally be taught in school. Approach one is this. You're gonna draw your ramp again, and we're gonna draw our object again. The idea now is we're gonna draw the forces. So we still know the weight. The weight is still vertical. So that's still mg going that way, right? But now our friction is along. Which way is friction gonna be? Friction will be along this way,
Parallel to the, yeah.
parallel to the surface. But is it going up or down the ramp in this case?
If the sled is going, or if that's going down, then the
Mhm.
friction is going
It should
up.
be going up, right? Because again, the idea here is it's at equilibrium. It doesn't. So the forces must be balanced, right? So I'll write that here, friction for now. And then the third force is that. It's kind of hard. I think it's easy to see here. Now what you can see here, and if you notice it properly, is that this and this are perpendicular to each other, right?
Mm-hmm.
Now, um, approach one is this, and this is how you draw it, and then solve it as is, right? Now, most books, I'm gonna say what most books do, okay, is that most books will do this. They're gonna go straight ahead and draw the x and y coordinates like that. So that's x and that's y. Okay. Now the problem here, the personal problem I see here, a lot of students have this problem, is that once they draw this and they know that this ramp is at an angle, in this case again, it's 30 degrees, right? The
Mm-hmm.
next problem is most students get confused to where the 30 degrees is. Okay, most books,
Yep.
again, let's write that there. Draw the x and y axis, then solve immediately, right? Now, again, the problem here is that most students who are still starting, so starting students
Mm-hmm.
usually struggle with identifying where the angle theta is. Students identify, struggle with identifying the angle somewhere else, right? In this way, 30 degrees elsewhere. Now, okay, in my case, because I've been working with this for so many years, I'm basically, I can see where the angle is immediately. That 30 degrees will be here. Okay. Now, um, now what my approach is here, okay, alternate approach. So the alternate approach here is to still do the same thing, okay. Uh, okay. Um, still identify your x and y coordinates, your x and y axes, right? But you do a second trick. You do a second, um, I'll just say trick, okay? I'll get to that trick later on. Okay. So the idea is if I copy that, I'm not gonna copy that straight away. Okay. So for example, again, let's draw the ramp like this, and that's 30 degrees, right? Then we draw our object again,
Mm-hmm.
and then we put the forces again. So mg is still gonna be like this, and then friction is still gonna be along the ramp like that, and then finally the normal contact force will be going up like that, right? Now the trick here that I that I always let beginner students do, and those who still struggle after a while, okay, is okay. I'm gonna take a screenshot to really show you what's happening. Okay, so where is that thing? Okay, so here is a copy of the same problem as a screenshot, right? What you're gonna do is you're gonna rotate the whole problem so that it looks more or less familiar to you. A vertical and horizontal set of
Mm-hmm.
axes. Okay, so that's the trick here. I'll add that here. Rotate the problem uh, so that the x and y axes are what you're used to, horizontal and vertical. Okay, now when you rotate the
Yes.
problem, you rotate the forces along with it. Okay, so make sure to rotate all the forces along. Okay, because what you're doing here is you're not changing the problem, you're only changing your point of view. Okay, so what happens here is when you rotate all of the forces along, so basically I'm just going to write it here on rotation. Oops. Okay, on the rotation, everything rotates by 30 degrees, right?
Yeah.
By 30 degrees. So what happens here? This is now, it basically rotated 30 degrees that way, went vertical. This rotated 30 degrees. So this means the weight also rotated by 30 degrees. Okay, so that makes it a bit easier to see. Once it's there, you do the same table. So next step is from before, you do the table, then you solve. Next step, table and solve. Okay, so how do we set up our table again here? I'm just gonna do that for now, x and y. So how many forces do we have here? Three. We have the friction, we have the
Yeah.
normal contact force, we have the weight, and then we do the mg. We do the positive and negative parts. So along f is negative because it's to the left. So I'm just gonna write that as negative f, right? That's 0, and n is just n. This is 0. Y positive, it's going up, right? And finally, mg is the one with components. Mg is the one with components. So if you look at mg, let's draw it here. That's your whole mg. So what are your components? You have your wy component here. That's your 30 degrees. And this is your wx. So finally, we just put that here. Wx is to the right. So that's going to be positive mg opposite sine theta, 30 degrees, right? Then wy is downward, so that's minus mg cosine 30 degrees. The sine and cosine, if you notice, they're not like normal. Normally we have x for cosine, and normally we have sine in the y value, right? So you have to be careful here with ramp problems that they're usually reversed. Okay. Then
Okay.
finally,
Wait. You said
go ahead.
um. Oh, sorry. Never mind. I didn't. No, never mind. I couldn't see the X and Y,
Okay, sorry.
so I was wondering why it was like.
All right. I
But
think
now it
I'll
makes sense.
I'll adjust the screen a little bit more so you can see that. Is that better?
Oh, I see it. It's good.
All right, great.
Yes.
Okay. So, what do we do now? Sum of forces on this side, right? Resultant force. We know the object is in equilibrium, so both of these would be 0. Equilibrium. Yeah. And now we're looking for the frictional force. We use x. So minus f plus 0 plus mg sine 30 degrees is equal to 0. And then solve for f. F is equal to mg sine of 30 degrees. Our mass, m, was given as how much? um 2.5 kilograms. Okay, I'm gonna so what we're gonna do here now, we're just gonna solve that right now. So 2.5, oops, sorry, calculator. We get 2.5 kilograms times g, we'll use 10 for now, 10 times sine of 30 degrees. So sine of 30 degrees, that's 1/2. This gives us 12.5 newtons for the frictional force. Okay, again, so is that clear?
You,
Or is there anything you'd like
so
to
you add
clarify?
the you add all of them
Yes,
basically.
yes, that's
Like,
right.
but where did the n go?
Oh, it's on the, it's here on the y
Oh,
coordinates.
n is
So
n. Um,
go ahead.
no, no.
Yeah, we can actually
Sorry.
solve for this n. We just do
Do
this.
we need it?
We at the moment for problem says no.
Mm-hmm.
Okay. However, we will need it later on to solve for something.
Mm.
Okay. I'm gonna continue with the problem later. But anyway, we will need n later on, so we'll still need to solve this later. But for the problem I gave you, we only need to do x.
Okay.
Okay. All right. Anything else you'd like to ask?
No, because all you did was just add it,
Mm-hmm.
add the x.
Mm-hmm. So again,
Yes.
so again, the only thing you need to do, and this is again for those who are still struggling to see how it works, is just rotate the problem. You change your point of view. You don't really change the problem. You just change your point of view. Okay.
Okay.
All right.
Yes. No question.
Okay. So, um, okay, this time around, I'm going to give you a similar problem. I'll ask for something else. Okay. You try it, and then we'll discuss how it goes. So I'm still gonna give you the ramp problem like this. Oops. Okay, I'll still give you the ramp. I'm still gonna say this is in equilibrium to make it easier. Okay. This time I'm gonna make that 20 degrees and the mass is equal to 5.0 kilograms. This is a rough surface, just like before. Okay, so the question is now, what is the magnitude? I'll type that one in. What is the magnitude of the normal component of the contact force?
Mm-hmm.
Okay, that's it. All right. So CJ, as you work, you can just tell me your final answer when you're done. Okay. Um,
Okay.
or just tell me if you're done, and then we'll go through how to solve it.
Okay.
Okay. Okay.
for this question,
Mm-hmm.
I find both the x and y forces, right?
You could. Uh, Actually, you just need to do it for y, just so we're clear.
Okay.
Okay. Um, but it's still a good idea to find both the x and y values for all the forces, or the x and y components for each force.
The weight would be -50, right?
That's right.
Okay. -50 cosine 30 for y, right?
Mm-hmm.
No, 20, I mean.
Cosine 20, correct. Okay,
Okay.
let me redo that real quick. That 5 could be mistaken for a 3 there.
Yeah, I was thinking it was a 3 as well.
Mm-hmm.
Okay.
Well, that's the thing with my handwriting. It's just messy. and and then you try writing on a very smooth surface like the surface of a tablet. Ah, it's even worse.
Yeah.
All right. Have an answer yet? Or close,
Um,
quite close, I guess.
I'm looking for the force of x. I don't need the force of x, right?
Not yet. No, not yet.
Okay, so I'll just do y then. Should it be a negative number?
The normal contact force should be a positive number.
Oh,
However,
this is I'm
uh,
finding the norm.
mhm.
Is it like 47?
Okay, let's see. Yeah, I'm gonna solve this again for the stream. So let's see how it goes. Yeah. So you got 47. Let's see
Okay.
if that's correct. Okay. So again, if we draw the diagram, I'm gonna draw the diagram right there. Um, the weight's gonna be vertical, same thing as before. Friction is in this case up the ramp still, and then normal contact force is still going in like that, right? So if you redraw that on a normal on a regular x and y coordinate system, what's going to happen is you rotate every other force accordingly. So this is now like that. The friction's here. The normal contact force is now up there. Now the weight has rotated this much, right? And we know the angle, that's 20 degrees. This is the weight. So this is going to be Wx and Wy. Okay, so we set up our table. What do we get? Friction and, oops, I forgot that label. And W, and then sum of forces right here. Okay, and again we do X and Y. This is going to be minus F, then 0. Then for N, it's going to be 0 for X, and then N. And then for W, this is going to be W. I'm just going to write mg. Okay, so that's going to be mg sine of 20 degrees. And this is going to be mg for y cosine 20 degrees, negative because it's going down. Both are in, it's an equilibrium, so both components are 0. Then we just solve for n. We can I'm gonna shortcut this, but I'm gonna point it out with the laser here. So 0 plus n minus mg cosine 20 degrees is equal to 0. So we're gonna write down n is equal to mg cosine of 20 degrees. We know our m, we know our g. We just put that in the calculator now. Where's the calculator? So again, mass is 5, g is 10, then cosine is 20 degrees. Take the cosine of 20 degrees. That's gonna give you 47 newtons. So you got the answer right. Great.
Oh, wait. I got the force pointing downwards. So then I thought it was the opposite.
Okay, remember that the contact force, the normal contact force, is always directed opposite the weight, more or less opposite the weight. Okay, that's because that's the normal contact force is the force that counteracts the weight, so that it doesn't really go up or down if it's not in equilibrium, or rather if it's in equilibrium. Okay, I think you got you still got the 47 though. It's just the negative that was a bit wrong, right?
Yes.
Okay. What's different from what I've done to what you did?
Um,
Maybe the signs.
I did negative. I get negative 50 cosine 20.
Yeah, it is. I do have negative here. So let me redraw that. I think that doesn't look negative. I have negative here.
I did the same thing then.
Okay, in that case, you're good. Again, what you have to do is 0 plus n plus negative mg cosine theta equals 0. Okay, you again just have to add them. Okay. All right, that means you're kind of getting it. Now, once you're kind of getting the hang of it, then you get to see this particular pattern. Once you get the hang of it, you don't have to do the rotation trick anymore. You just know where where that angle is already, right? Okay. All right. I'm gonna give you a different problem now. Still in equilibrium to make it easier, but I'm gonna revisit the first problem. Okay, just as an example. So if we revisit this problem, oops, just take a screenshot to make it a bit easier. Just that. Okay. Now, if we revisit this problem, we know that the frictional force was already solved beforehand. And, okay. Okay. I'm going to add a different problem here now. Okay. So with this same information, I can ask you the exact same thing. Or rather, I can give you the exact same thing and ask you a different problem. The question now is, what is the coefficient of friction between the ramp and the block? Coefficient of I'm gonna put the word static in here already, but the coefficient of static, I'll explain later what that means. Okay, so what is the coefficient of friction between the ramp and the block? Okay, now for you to answer this, one thing, this is the definition. Okay, the frictional force is equal to, well, I'm just gonna say equal to for calculation purposes. Okay, so friction is equal to this number times n. This is the coefficient of friction. The bigger this is, the more friction there is between the two objects. Okay,
Is the coefficient always given?
sometimes you have to solve for it, like in the problem I just gave you. Okay, however, the coefficient of friction, before we continue, the coefficient of friction is basically a number that tells you how rough the contact between the two things are. The bigger the rougher the contact, the bigger that coefficient of friction. Okay. Um, okay, so let's take a look here. We have previously solved it by we're not gonna solve it again because we already did part of it, right? Here. We've already done the solution to that with this. So let me just take a quick screenshot here and put it back here. Okay. All right. So in order for you to determine the coefficient of friction, this is where you need the two components to come along, okay? So in our case, we already solved for F. That's going to be mg sine 30 degrees, right? So if we put this here and make our equation, we basically now get n minus mg cosine 30. Oops, this is negative. Oh, never mind, it is positive. Okay, mg cosine 30 is equal to 0 as well. So we get n equals mg cosine 30, right? Okay. Now, you will notice that I am solving this without actually looking for the values yet, right? Okay. The reason for that is because the frictional force is equal to, again, mu n. Okay. So all I'm going to do here is I'm going to put the values in. Mg sine 30 degrees is equal to mu times mg cosine 30 degrees. What cancels out?
Um. Oh, wait.
Yeah, the weight cancels out. Mg cancels out, right? So from here, we can solve this now that mu is equal to cosine 30 degrees all over, other way, sorry, sine of 30 degrees divided by the cosine of 30 degrees. And that's going to give you tangent of 30 degrees, right? So that is how you solve for mu. You always start with this definition and whatever values you're given here. Okay. A lot of the time, not all of the time, a lot of the time you'll end up canceling stuff out, significant stuff out. In this case, we did. Okay. So once we have this, all we have to do now is find the tangent of 30 degrees. So 30 tangent would be 0. So in our case, our coefficient of friction is 0.58. The coefficient of friction is dimensionless, so the number is just a number. Okay. All right. Okay, is that clear?
Yes.
Okay. Okay, I want you to redo now the problem you got earlier with this problem, right? Oops.
Yeah.
And this time you find the coefficient of friction between the ramp and the block. So, okay, I'll just duplicate this. Duplicate data. Okay. Just copy this to make it easier for you to do.
So what I do is mg sine 20 equals coefficient of friction. No.
Yes. Okay, carry
but
on.
Isn't there the friction on the x-axis?
Yes. Okay, but in this case, that formula doesn't really tell you direction. It only tells you what the proportionality between F and N are.
Okay. Do you think friction could be on either side of the equation?
In reality, yes. It depends on your point of view.
Okay.
Okay. But usually we just have one frictional force to represent all of the frictional forces acting on the object. Okay.
I got 0.364.
0.364. Okay. I'm gonna just do a shortcut and just say that that's tangent of 20 degrees. So 20 degrees. Find the tangent of that. Yep, correct. 0.364. Okay. I'll just show you real quick and again how this is done. So F equals mg sine 20 degrees, and then n is equal to mg cosine 20 degrees, and from here F equals mu n. So this is mg sine 20 degrees equals mu mg cosine of 20 degrees. So again, same thing exactly happens. We're left with mu is equal to tangent 20 degrees. Okay, and that leaves you with 0.364.
Yes.
Okay.
Why does mu mean like 3 different things?
Because that value basically depends on on the situation between the block and the ramp. Okay.
Okay, I
However,
mean like
go say it again. Oh, why
mu
are
is
there
like
three values, right?
yeah, like the unit, the mean, and like coefficient.
Oh, okay. That's because okay, so we got the equations out of the way. We kind of solved it and we understand the solutions, right? The question now becomes why do we have that? Why do we have that? Why do we have that? Correct? Okay.
Yeah.
The reason for that is this. I'm going to start with approach 2. This approach 2 actually is the correct physics, but it's a bit harder to do the math with it. So that's why we do approach 1 with the math. Okay? So approach 2 is the correct physics, correct, but harder to do physics, a harder math. Okay? Okay. The key idea here is that if you're on the ramp, if your object's on a ramp, there are only two objects here. We have the ramp and we have the, let's say the box, right? So because there are only two objects, there must be there must be an action reaction pair. Or better yet, I'm gonna start with the box. If the box is in equilibrium, if the box is about to get out of equilibrium, in other words, it's at equilibrium, but just a little more push, it's gonna slide, right? Equilibrium. In other words, about to slide. Okay. Then that means. Okay, let me just fix that. Okay. So while I'm fixing this, so it's about to slide. Then that means the forces forces just about balance out, right? Balance out exactly, right? It's not one way or another. Now, the idea here now is if you're going to be really strict on what's happening, there are actually two forces on the box and not three. Again, there are two forces on the box and not three. What's the first force? Weight.
Gravity? Oh wait, sorry.
Okay. Yeah. Okay. And what's the second force? I'm just going to label that F. Okay. Where this F is the overall force exerted by the ramp.
Yeah.
Okay. So you see here, I'm not talking about friction. I'm not talking about what's this about the normal contact force? I'm just saying that there's a force that the ramp is exerting onto the box, right? And in this case, um, F equals mg because they balance out exactly, right?
Yeah.
Okay. So this is where the frictional the frictional component and the normal component come in, because in this case, now that we have that particular setup, you can think of this as this is going to be fx, the x component of f, right? And that's your frictional force, and then your fy is going to go that way, and this is your normal contact force. Okay, and where's our angle? If this is our angle, then similarly our angle here will be here, theta, right? So what so let's write that again. So we have F equals mg. What is fx equal to? Fx is equal to sine f sine theta, right? And then finally fy, that's gonna be f cosine theta. Of course, we'll label that now. That's the frictional component, and this is the normal component. Okay, so you can already see what is f over n. It's gonna be equal to tangent theta, and this by definition, in other words, we defined it to be, okay, is equal to mu. Yes. Okay, now I put the label s. All right. Okay, so is this a bit clearer in terms of explaining what's actually happening? We just basically took the ratio between the two components of the actual force counteracting the weight. Those two components happen to be the frictional and the normal components. Okay, now
I think I need a question to understand it better.
okay, say that again. You got cut off for a while.
Sorry, I think I need like a question to practice.
In this case, we don't need to practice this. This is just to explain why we get tangent theta in our calculations.
Oh, okay.
Okay, so we don't need to go back and practice this. Okay, now the next thing I want to go to is this. I kind of wrote mu s, not just mu, right? Okay, because mu, the coefficient of friction, has three variants in physics. There are more than three, but the three most common ones are mu s, mu k, and mu r. Okay, this is the coefficient of static friction. Coefficient of static friction. Okay. I did static twice. Hold on. Okay, that's the coefficient of static friction. The second one, mu k, is the coefficient of kinetic friction. Okay, kinetic. And the last one is the coefficient of rolling friction. Now, for us in DP, we only need mu k and mu s. Okay, so in DP, this is not, oops, hold on. Okay, this, not again. Hold on, what's happening here? All right, hope this works. There. So not in DP. Not in SL at least. Okay. So we can forget about this for now. Now the idea here is that the coefficient of static friction is what tells you the coefficient when the object is stationary. Okay. Coefficient of kinetic friction is the coefficient of friction you need when the object is sliding. And of course, rolling friction, this would be rolling objects. Okay. Now, you have to be aware of this relationship because this will be this can be asked later on. Mu s is always greater than mu k. That's the first thing that you should know. Okay? And then the second thing here is that the complete equation is this. F is less than, oh wait, okay, F is less than or equal to mu, sorry, why did I say F like that? Friction. The friction is less than or equal to mu s times n. Okay, this means that for an object that is still in equilibrium and not sliding, the maximum value you can get for friction is mu s times n. You can have smaller values than that, and that's acceptable. Okay. However, for equilibrium, right? Not equilibrium, but static, stationary. Because you, okay, stationary. Okay, and then the other one is the frictional force is always equal to mu k n for sliding. Okay. Why is it always equal to? Because of the fact that the friction can slow down the object later on. Okay. All right. So, okay. So with this, let's look again at another ramp problem. This time I'll make it a bit more difficult. Okay. All right. So here's
Okay.
our new ramp problem. Again, I want you to go with this with the first approach to make it easier for you because you're quite used to it already, right?
Maybe.
So maybe let's see. Yeah. Let's say that let's make this, let's still make that 30 degrees. Okay. And then let's say that this mass, the mass here, gonna be 1.7 kilograms. Okay. And then I'm just gonna give you a situation. Okay. Okay, that's it. And then I'm gonna say that the ramp is smooth. Okay, never mind, not smooth, it's rough. Okay. The ramp is still rough. Okay. The question is, I'll give you mu equals 0, mu s. Okay. 0.4. So the question now is the box gonna move or not? Is the box going to move or not? Okay. You still do the exact same things. So okay, I want you to do the everything else, and then when you get stuck, you let me know, and then I'll help you out. Okay. So the beginning step, all the starting steps here are identical to the first problems we've done. Once you get stuck, you let me know. That's where we'll continue. Okay.
Okay.
All right. I think you're getting used to the idea of using the table to solve problems.
Yeah, I'm doing the table right now.
Good.
X is sine in this case, right?
Correct.
Would y be negative mg cos? No, it's just mg cosine.
Y would be negative. You were right. It has to be negative.
Okay.
This SciShow video
Okay, looks like you're a bit stuck there.
Wait. Um, is so F is mu times R, but to find R, do I find the Y? Then like
Yes, yes. This
so
is where, good, you figured it out. This is where you actually have to use the two sides of the table now. You have to find x coordinates and you have to use the y coordinates to find this coefficient of friction, or
for
better
both
yet,
sides.
on both sides, or better yet, to find what the actual friction is.
Is
Okay.
the friction 5.9 by any chance?
Okay. I'll do that right now in my head for now.
Okay.
um, Actually, I can't do that in my head. I'll just solve it here. So I'm gonna go straight to the table because I'm pretty used to it already, right? So
Mm-hmm.
friction N W. This is gonna be mg sine 30 degrees. This is negative mg cosine 30 degrees. This is still you used r, so I'll use r with like you did. Okay. Now this is f, and this is
Not negative
0.
F?
Well, it's negative f, right? Okay, it's negative f, and that should be equal to mu r, right?
Yes.
Okay. So what can we find?
So if mu is 0.4,
Mm-hmm.
I thought I just do negative mg cosine 30
Mm-hmm.
and then just make it positive, the absolute of that.
Okay. The what I'm gonna do here is solve for y already, right? So r would be mg cosine
Yes.
30, right? And this is already solvable. Let's just put that in. M is 1.7. 1.7. So calculator times. Let's use 10 again for g. Okay. 10 times 30 degrees cosine of that. Now, for the more mathematically inclined people out there, that's just root 3 over 2. So you can just put that in. So in this case, our R is 14.7 newtons, right? Okay. Now,
Mm-hmm.
I would approach it like this. What is F via formula? Via formula, right? Okay. That will be
Uh,
equal to 0.4 times 14.7, right? So if
mm-hmm.
we multiply this 14.7 by zero point 0.4 times zero point 0.4 over here, we get 5.89.
Yay.
Okay, so you got this bit, I think, right?
Yes.
But that doesn't quite answer our question. Is the box going to move or not? Right?
Oh. Uh.
Okay. In order for us to find that, we need another f. We need the f now equals uh, the x part, this. Okay. So f should be equal to mg sine 30. Right? Okay. Later on, I'm going to show you how to finalize this. But once we calculate this, so again, our m is 1.7. So 1.7 times g is again 10, then times 30, sine of that. For the math inclined, that is 1/2 already. But let's just do it like that. That's going to give us 8.5. Okay. Now, this is the actual friction. Okay. This is the actual friction. This 5.89 via the formula. So F formula equals 5.89. Okay. This is the maximum. Yeah. This is the maximum friction. Oh, sorry, not maximum. Minimum friction needed to keep it in equilibrium. Okay. Why? Because remember that this is actually if you use the formula, it should be less than or equal to that, right? Okay, so what's actually happening? According to this, the actual friction is 8.5 newtons, but your friction just due to the situation, given the coefficient of friction is 5.89. So in this case, F is larger than FF, F formula, right? Okay. Um, okay, let's kind of put that, let's complete this. This is the actual friction needed, not present, but this is the actual friction needed for equilibrium, right? Okay, is your friction enough to provide equilibrium? F, actual friction needed, and okay, I think I'll confirm that further. This is the friction actually provided. Um, I think I'll remove the word actual just to keep you not so confused. So 8.5 newtons is the friction needed for equilibrium, but this 8.9 is the friction actually present in problem. So you see now, is the friction needed, sorry, is the friction given, the friction in the problem, does it get to the level that is needed to keep it in equilibrium? So again, we need 8.5 to keep it in equilibrium, but the problem can only give you 5.89.
So does that mean it keeps moving?
Yes, so in this case, the object or the box, so in this case, um, F is larger than F from formula, right? So this means not enough friction provided. Friction for equilibrium. Equilibrium, and hence box moves. Okay, makes sense.
Yeah.
The formulas, I think the two formulas make sense. The hard part here is actually converting those two numbers into an interpretation. Okay, so okay, let's do another one. I think I'll give you the exact same problem with different numbers, and we'll see whether it's an equilibrium or not. Okay, so you do it.
Okay.
All right, so this time around, this is 2.2 kilograms. The angle is 40 degrees. Okay, equilibrium or not? Rough contact. Okay, I'm gonna try something now, see if this is gonna work. Okay, so there's rough contact. So, um, is there, um, is the box gonna slide or not?
We'll see.
Okay, all right. This is what I'll do as you solve that. I will actually just uh look for some paper right here so I can do some paper and pen solving. Hold on. Okay. Oh, I forgot to give you the coefficient of friction, right? So let's say
Mm-hmm.
coefficient of friction is 0.5.
To find R, is it
Uh-huh.
mg cosine 40?
Yes.
Okay.
Okay, correct. Okay, I think you're getting used to it. All your questions have been answered with a yes for the most
Yay.
part. Yeah. Okay, good.
For the most part.
Mm-hmm.
I think I found the friction.
Okay, remember you have to find two values of friction.
Yes, the first value of friction.
Mm-hmm.
Mm.
Okay. I'm gonna show you a better way to solve this later. Okay.
Is the actual friction 14?
Nope. But close. There is a 14 there somewhere.
Oh, for the first friction,
Mm-hmm.
I got was um 8.43.
8.43. No. Hold on. I'm solving that. I'm still solving that. Okay. Okay, that's not gonna quite work. All right. So um ah okay. All right. I think I found a more mathematically rigorous way to do this now. So
Oh, thank you.
okay. So, okay, let's make this more mathematically rigorous. Okay, so because earlier we're just like comparing, right? So,
Mm-hmm.
uh, you said before you already set up your table, right? So I'm gonna do that here, x and y, uh, then frictional force. You used R, so I'll use R, and then W, and then sum of forces, right? Okay.
Mm-hmm.
Now, this is still gonna be negative F, and that's equal to negative mu n, right? Mu R. This is 0 here, right? Then for R, x component is 0. This is R. And then we have the same thing, mg sine theta, sine of 40 degrees here, and negative mg cosine 40 degrees, right? Here's the here's the mathematics that would make it a bit easier to do. Along the y direction, the object still is never moving. So that's going to be 0 here, right? However, we don't know if along the x direction it's going to move or not. It's going to accelerate or not. So we're going to keep that ma. All right?
Mm-hmm.
Okay. So if we solve the y components now, what do we get? If we solve the y components, we get r equals mg cosine 40 degrees, right? And that is equal to 14.14 newtons. That's your r. Okay? You are given your mu, so your friction is half of that, right? So 7.07 newtons. Okay, I'll just put it here like that. F is equal to 0.5 times 14.14 newtons. Okay. Um. Okay. So far clear. Same as before, right? Now what we're gonna do is we're actually gonna put our values in here. So we're gonna do what? So we're gonna get 7.07 along the x direction plus 222. I'll just put 22 now for mg, then sine of 40 degrees, right?
Mm-hmm.
That's gonna give you 2.2a. Okay, so now we can actually solve for a. We just divide everything by 2.2, right? So we get
Is
7.
A just acceleration?
Yeah, the acceleration. So we put here negative 7.07 over 2.2 plus 10 sine 40 degrees. And that's equal to A. If A equals 0, equilibrium. Yeah?
Yes.
Okay. So that's what we check now. Is A 0? If A isn't 0, it's going to accelerate downwards. Okay? So if we put that in the calculator now, what do we get? Where's my mouse? Here. Okay. 7.707 divided by 2.2. That's gonna give us that much. Then plus 10 times 40 degrees. Take the sine of that. Boom. Acceleration is not 0.
Yes.
So the object is going to move. The box is gonna
Yes.
slide.
Wait, does that mean it keeps accelerating, or is it accelerating at that point?
It's gonna accelerate at that point, and then what happens afterwards depends on the value of the coefficient of kinetic friction. So it just starts accelerating because we start from static friction, right? right?
Mhm.
So once it starts from from static friction into kinetic friction, it's gonna keep sliding. Now, is it gonna keep accelerating? It depends on the value of the kinetic coefficient of kinetic friction. But in general, because it's smaller, yes, it's gonna keep sliding and keep getting faster. It's gonna keep accelerating,
Mhm.
which is true if you actually try to slide something down any kind of ramp, right? If you want, you can try that yourself with like a box or something. Hold on, I have here a piece. Okay, I'm gonna go to my main board, main camera first. Okay, so I have here this plastic sheet.
Mhm.
Okay, now I'm gonna move this. Okay, what object can I use? SD card should be okay. Okay, now here's the thing. I'm gonna keep putting it up like that until it starts sliding, and see what happens. It starts sliding, and then it keeps getting faster and faster. But if I keep adjusting the angle so that it kind of jitters around, it doesn't matter. But here, if the angle is already too big, no matter what you do, it's gonna accelerate.
Yeah.
Okay.
Does the friction increase or decrease as you
Uh,
accelerate?
it doesn't. It changes value once you start accelerating. So at the beginning, it's let's say zero point 0.5. Then once it starts moving, let's say it goes to zero point 0.4, right?
Uh,
Um, as it starts moving, no, not as it starts, as it keeps sliding, it's gonna stay at zero point 0.4.
okay.
All right. Okay. So is that it? I think that's it for that particular problem. Okay. I'll give you one last complicated problem.
Mhm, mhm.
Okay. And
Okay.
then we'll move on to Suvat. Okay.
Wait. So quick question.
Go
Sorry.
ahead.
For the whole total friction, you do mg sine theta.
If the angle of the ramp is given from horizontals, just like this. If the angle is given like this,
Okay.
okay? If the angle is given from, let's say here, from vertical, then that changes the problem a bit. You just switch the cosine and sine,
Uh,
okay?
but if the cosine is given like that,
Mm-hmm.
we could literally just find sine.
Yeah, you could.
I mean, we could just find the missing angle.
Yeah, we can actually. In my opinion, it's actually easier to do it the way you said it. So let's say that if this was the given angle, let's say that's 50 degrees, right? I'm gonna look for that 40 degrees first before I solve anything else. Because as you said, it's easier because you're used to that particular angle being measured, right?
Uh-huh.
Okay, so of course the
But if it
technique,
was 50, then I would do um cosine. No, I would use cosine, right?
yeah, if you're gonna keep it at
Okay.
the 50, then you're gonna switch the cosine and sine. All right,
Is it the horizontal friction, or no, is it just
just friction.
okay?
Okay, all right, ready for the hard problem?
Where
I'm gonna add a force at an angle. Okay. All right,
mhm.
because there are some problems in the book that are easier than what I'm gonna give you. Also, problems in the exam that are easier than what I'm gonna give you. Okay, so this is the most difficult possible problem you'll encounter. You have your ramp, you have your object, you have a pulley at the top of the ramp.
I always get this one in my tests.
Yep, you should, right?
Yeah.
Okay, and on this pulley, I'm not gonna make it more complicated than this. This is the hardest one you'll get in an exam. Okay, this pulley is like that, and this is a mass. Let's give these masses some values. Uh, 3.0 kilograms and 4.0 kilograms. Okay. Again, let's make the ramp rough. Okay, so unfortunately, because of the nature of this problem, you don't know which way it's gonna go, right? But I'm gonna give you that mu is equal to 0.3. Okay,
Mm,
all right. So the question is, which way, which way is the 3 kilogram object gonna go, up or down? And what is its acceleration? Okay, so which way will the 3 kilogram object move? Okay, and then the second part is, what is the acceleration of the 3 kilogram object? Okay, you need the hit. You need the. You need hints before you solve this.
let me try first.
All right. If you get lost, tell me. I'll give you some hints. Yeah.
Yeah.
All
Okay.
right. But again, I'll give you one hint now. You're gonna have to set up 2 tables. That's it.
2 tables.
Oh, I forgot the angle.
Okay.
Hold on, I forgot the angle. Uh, let's give this an angle of. Let's keep it again at 30 degrees.
Hmm. Okay.
Okay, I'm gonna solve it here on my window first while I wait for your answers. Hmm.
Wait, what's the point of drawing it out if I
Hmm.
only use the table?
Okay, the point of drawing this out, um, is it helps. Basically, once you get used to not to reading the diagram, you don't need to draw it much anymore. Like me, I don't
Okay.
really draw it out anymore, right? But
Mhm.
the drawing is for starting students. It's actually a very useful tool to visualize the problem. Okay, what I normally do is I still draw the problem, but I don't draw the free body diagram anymore. I still draw the actual problem though.
Hmm.
Okay, uh, right. Hmm. Do, is there something you don't actually need? Yes, there's something you don't actually need.
So to find R, 40 sine 30 or 40 cosine 30?
Uh, find R, right? Cosine.
Yeah. Sine.
Mm-hmm.
Sine.
Cosine.
Okay.
Cosine. Cosine.
Cosine.
something. That's what I forgot. Okay, I forgot something. That probably means you forgot something.
What?
Yeah, I forgot a particular value in my table. So that probably means
What
you
I
forgot
forget?
something.
Oh, is there a normal for an X?
No, but there is a fourth force on X. Or a third
Yeah.
force.
Is it the string?
Mm-hmm, exactly.
Okay.
Okay. All right. So from here, we get this. Where's my phone?
Wait, so when you find the friction force,
Mm-hmm.
not like total, but like the one friction,
Mm-hmm.
is yours like um 10.4?
Yep. Correct so far.
Okay.
Correct so
Now
far.
from that value, what do I do
Mm-hmm.
next?
Now from here, all right, let me just put on my notes. You got this. You probably got this. The F. I'm not gonna put the sign, so I'm just gonna put absolute value, right?
Mm-hmm.
10.4, right? And then your N, you got that as 34.69 or 64. Was it 69 or 64?
34.6.
4.64, right? Okay.
Yes.
Uh, okay. What you do now is you find, um, well, you don't really know whether the object is sliding up or down the ramp. So that's the problem with this F. Is this gonna be plus or minus, right?
Mm-hmm.
Right? Okay, so what you will do is you will assume in your diagram a direction. You will assume a direction for the whole thing. Okay. Uh, okay. So, okay. So what you're gonna do now is okay. I'm just gonna write this down from what you have. I'm going to assume that the friction is positive, right? So
Mm-hmm.
F and W and tension, and that's sum of forces, right? We're gonna
Mm-hmm.
focus on the X part first. We're gonna ignore Y because we just used Y, right? So what I'm gonna do is I'm gonna assume that F is positive, N is 0 here. This is gonna be 40 sine 30 degrees. You got this probably, right? And our tension is always gonna be directed to the left, or well, to the negative X direction. So that's gonna be minus T here. Okay, and this is gonna be equal to 4A. Now, the thing is, we're gonna look for T, right? But earlier, here, we also have another set of equations for there. We basically get T minus 30 is equal to 3A, right? That's
Mm-hmm.
important because here we can now say that T is equal to 30 plus 3A, right? And we're gonna put that T in there, okay? Now, if we're gonna put that T in there, okay, we're gonna say that this is now negative 30 minus 3a, right?
Wait, why is it a 2F with a line on top?
This one? No, that's not 2f. That's sum of forces.
Oh,
Okay,
okay.
let me clarify that. Okay, so now that we have that, we're going to solve for a. So f minus, f plus, let's just put that in there. What's sine 30 times 40?
Why is it 4A?
Mass times acceleration. The mass is 4. It accelerates acceleration a, right?
Mm-hmm.
Okay. Let's do this now. So 30, take, why is the calculator not working? Let's do that again. 30, take the sine of that, times 40. That's going to give us 20, right? So f plus 20 minus 30 minus 3a equals 4a, right? But we have our, we'll take a look at the friction first. So friction will be equal to, friction minus 10 equals 7a. And therefore, we now have like some sort of formula, right? Now, the thing here is, if f was positive, that means it's going to go down the ramp. That means the acceleration is going to go up the ramp. That kind of gives us a positive value. So I'm going to write that here, okay? So if f is that way, so let's copy the formula first. F minus 10 is equal to 7a, right?
Mm-hmm.
Okay, so this would tell us if f is this is positive, we're going to use the positive value. So we're going to use 10.4. Sorry, this is supposed to be plus, right? Yeah, supposed to be plus. Oh, sorry, minus. You're right. I was right. Minus. So 10.4 minus 10, right?
Yeah, sorry.
Okay.
Where did F plus 20 minus, like, F plus 20 come from?
Let's go back here. This is the F, right? That's the F.
Mhm.
This 20 is the whole 40 sine 30.
Oh, okay.
Okay. And then, of course, this is the tension from here going in here. Okay. All right. So if F is going this way, then F is positive. Then minus 10 equals 7a. 0.4 equals a 7a. And from here, the acceleration is 0.4 divided by 7. 0.4 by 7, calculator, is equal to, oh, let's do that again. 0.4 divided by 7 is 0.06 positive value, right? Now, if f is up the ramp, what do we get? Negative 10.4 minus 10 equals 7a. And therefore, the acceleration will be equal to 20.4 divided by 7, negative. And that's going to give us what? 20.4 divided by 7. That's going to give us negative 2.91. Okay, meters per second squared. Meters per second squared. So the answer now depends on what's the more realistic situation. Is the friction going to go down or is the friction going to go up?
Up? No.
Think about it. Think about it.
Going down.
Friction is always going to oppose motion, right?
Oh,
So
really?
if it's going to be pulled up by the tension and it's going to be pulled down by the weight, which one is the winner? Whatever the bigger force between those is, the friction's going to oppose that, right? Okay. So so now what we're gonna do here is the best thing to do is to substitute these values back into here to find an actual tension.
Wait. So the 0.06 acceleration, is that to pull it up or down?
This pulls it down. Pull down.
Okay.
Okay. This pulls up, right? pull up. Okay, so the best thing we can do, because we're still not sure which one it is we're gonna have to put these values back into the tension equation. Tension minus 30 equals 3a, right?
Mm-hmm.
So finally, we have these possible values for a. What is the actual value for t? So if we put that in, t would be equal to 30 plus, let's put this here first. T equals 30 plus 3a. We put our values of a in. So the first one is uh, t is equal to 30 plus 3 times negative 2.71, 2.91, right? 2.91. And the other one is t equals 30 plus 3 times 0.06. We get two different values of tension. Let's, what are the two values? 2.91. Let's put that here. 2.91 times 3 plus minus 30. It's going to give us 21.27 newtons. This is up, right? And then the other one is going to be zero point zero 0.06 times 3. 0.06 times 3 plus 30. In this case, 30.18. So the tension in both cases is going up, right? So tension goes up. So this is where we finalize the interpretation. Like I said, this is more difficult than what you normally get, right? Because we're gonna have to look at different cases. But that means either case, the tension is upwards, right? So the
Mm-hmm.
tension here is up there. That means the tension here is gonna be up there. And then finally, our object is gonna be here. This is our 4 kilogram object. Um, it's gonna be pulled this way. So we know that so it depends mostly now on what the tension actually is. Okay? We Because we don't know what the actual tension is earlier. Okay? If in most problems, so both of these are correct. Okay? Both of these are correct. However, in problems you would get in a paper, you would be given one of those tension values, and then you should be able to solve whether it's gonna go up or down the ramp. Okay?
Mm.
So going back to the problems here, the answer is actually depends on other factors, right?
Yeah, by the way, is the 30 from for the t minus 30, is that just the angle?
No, the 30 here is just 3 kilograms turned to weight.
Oh, okay. So t
Okay,
minus mg. Okay.
okay. So t minus g. All right. So again, this was a trick question. In all honesty, I was already thinking, okay, this could be a trick question. I just want to confirm. But yeah, trick question.
Aren't there two functions?
What?
Isn't there like a t plus mg?
Okay, the idea here is this, okay? I'm gonna draw that again. What does that mean? If the tension is the lower value, right?
Mm.
Then that means the object is gonna slide that way if the tension is gone. So that means that the friction is acting this way. Okay,
Mm.
all right. If the tension is of the higher value, let's put that here. If T is in the higher value, right? So this means that T and F counteract the weight, right? If T is the higher value, then how would that look like in the problem? So that's your pulley. This is your thing. That's your object. The tension is still going this way, but this time the friction is going that way. That's what it means. So T counteracts both W and F. Okay, so those that's what the problem actually means in this case. In other words, you solved it, but there's no satisfactory answer to it with the way I set up the problem. Okay. Now, last thing about this IB again, I just want to say this before we end, before we go to Suvat. Yeah, we have some time for Suvat, right? So, IB problems, question problems of a similar nature, right? If you have your ramp here and you have your object here, normally T is given. So instead of determining whether the objects are gonna slide up or up, okay, doesn't you will be actually be able to solve it. Now another thing that's normally given is direction of motion, usually given. Okay, is normally given. Now if you know the motion, then that means you know the direction of the friction. It will oppose that motion. Okay, so friction opposes this motion. Okay, all right. All right, so I think we're done here for now. The other problems, I think you'll when you get to the other ramp problems, should be easy enough to solve. Yeah.
Okay.
All right, so I'm just gonna open a new Jamboard because I ran out of
Wait, is
space here.
motion one of the ones where it's like the distance between like how high do you have to hit to get over the net like that?
That's gonna be under Suvat.
Okay, because I would like to focus on that because I'm
Okay,
really bad at that.
right. Okay. That's actually pretty easy again. We're still gonna use a table, but the table's gonna set up a bit differently. Okay.
Mhm.
CJ 25 Jan 2024 part 2. Okay, so here's the new Jamboard. I'll just share with you the link. Mhm. Okay, here's the new link. Um,
Thank you.
Suvat. Okay, the table you're gonna set up another table for Suvat again. But before we go there, you already know the equations from the data booklet, right? Okay.
I think so. Yes.
Okay. If you don't memorize the formulas, it's fine because they're given in the data booklet. But I'm just gonna write them here for our reference anyway. So again, the first equation is V equals U plus AT. Second
Mhm.
equation is S equals UT plus 1/2 AT squared. The third one is V squared equals U squared plus 2AS. And the fourth one is S equals U plus V over 2 times T. Okay. All right. Uh, I've discussed this before with you, but I don't think you'd recall them. It's because it's been a while, right?
Mhm.
But the another thing that is gonna be useful for Suvat before we go to how to solve them is the tech is what how you actually solve it. Okay. Look for
Mhm.
the equation with three knowns and the one unknown. Okay, use that. So I'm gonna say not look for but use. Okay, use the equation with the three unknowns, with the three known quantities and the one unknown. Okay, now the last thing we're gonna do is how to set up the table. Okay. Um, in projectile motion later on, it's gonna be useful to do x and y again. So we're just gonna generalize it to x and y again. Okay. Now what am I gonna do? I'm gonna write suvat just like that. But you will notice that when I do this, I'm gonna erase something. I'm gonna erase that.
Oh, that makes sense.
Right? Why? Because the time for x and y will happen at the same time. Whatever's gonna happen in x is gonna happen at the exact same time as y. Right? Okay. So this table is for is for projectile motion only. Yeah. One-dimensional motion, it's very easy. You don't need the table. Okay. Okay. But to make it more consistent, I would suggest that you would use the table whether you're doing one or two-dimensional analysis. Okay. So, here's the thing, and this is automatic. Okay. G, the acceleration in y is always gonna be equal to g. Okay. That's the only thing that you need to remember aside from the setup of the table. This has to be there. Everything else can assume any value. Okay. So what does this mean? So let's you want to go straight to projectile motion or take it like x and y directions first? I think let's go x and y. Let's do x first, okay? So horizontal motion first. Okay, horizontal motion. I'm just gonna give you a quick one. In fact, this is gonna be easier if I just look for an internet problem here now. Equations, problems. Okay. Where's a good one? I think this is good. Okay. For our reference, I'm looking at the University of British Columbia files here. Okay. All right. So here is the first problem. This is all horizontal motion for now. Okay. So you have a car beginning from a stationary position and it accelerates at 4 meters per second for 10 seconds, then travels at a steady speed for another 10, all in the same direction. So in these 20 seconds, how much distance has it covered? Okay, we're looking for distance, right? Okay, so again, just to form the habit, I'm gonna put the suvat table in, but we don't really need the x and y label, so I'm just gonna write suvat like that, right? Okay. So do we know our s? We don't.
No, that's what we're looking for.
Okay. Now what is our u? Stationary.
0.
Stationary, so 0. Our v is, we don't know as well, right? Okay, our a is what?
4.
4. And our t is?
Is it 10 or 20?
It's just 10. Because you have to keep each stage separate, basically. So stage 1 like that.
Okay.
Stage 1, stage 2. Okay. Stage 2, we also don't know s, question mark, right? But we know whatever this is equal to, I'll just put that here, right? We don't, and then because steady speed, then we know our v is also going to be this, right? Now, this means that the acceleration in this point is 0. And we know as well that the time it takes for that is 10 seconds, right? Okay. So the difference now between SUVAT and the forces earlier is the equations here are not pretty straightforward. You don't just copy and done. You really have to look at the formulas and see which ones have what you need. But this still helps because let's take a look at the equations again. Take a screenshot here for our reference. Okay. So for our reference, we can see here that we have U, we have A, we have T, we're looking for S, right? Right? So the first part is that we're looking for S. Which one has SUAT? It's this one. So part 1 is we use S equals 0 times 10 plus 1/2 times 4 times T 10 squared. So that's going to give us that's going to be 0, that's going to be 2, that's going to be 100, it's going to give us 200 meters. Okay? S is equal to that, 200 meters. Now the second step is looking for this V so we can put it in here, right? So it's still here. So we're going to use, this time, while we are not interested in S on the second part, right? So we're now interested here. So which one has those four again? Which formula has those four? UVAT. It's now for part 2 that. So part 1 is that. Part 2 is
V.
that. VUAT, right? So we don't know V. We keep that as V. U is 0 plus A is 10. Sorry, not 10, but 4. Okay. 4 times T is 10. So V is equal to 40. So we can now replace that, right? So we now know that this is 40.
Mhm.
Okay, 40. And this is also 40. Now, we are looking for S again, right? But what can we do now to find this S? We actually have we can use any of these, right? Which one is the most useful to find this? It's gonna be this, this, this. That's gonna be for number 3. So 3.
Mhm.
That's basically gonna be 40 plus 40 divided by 2. That's still gonna be 40 times 100. So for 3, that's gonna be S is equal to 40 times times 10, right? And
Mhm.
that's gonna give us 400. Okay, meters. So the final answer is you put those two answers together. This is 200 meters. Just put it here, 200 here. We have 400 here. Total distance is 600. Okay, so again, it's not really different from what you've learned before, but again, it arranges everything so you see which ones you're looking for. All
Mhm.
right. Okay, so let's do one horizontal motion problem. Let me get the problem from the same spot. Okay, no, not that. Okay, now again, what we want to practice here is the use of the table to help you solve, right? Because I know you can solve these problems already. Now, in this case, this problem, you have to look at this carefully. Is this horizontal or vertical? Okay, you solve this on your own using the same technique. Yeah. But if it's vertical, again, if it's horizontal, you need a value for the acceleration. If it's vertical, then
We already
uh
know it.
yeah, you should know it. Um okay, I'm gonna add a secondary question to this, yeah. Uh and Okay, there. Let's add that. This
Is
one,
the first equation u plus v divided by 2?
okay, I'll just copy the equation again. Yeah,
Oh,
just copy
okay.
it again. Control C, Control V.
V squared equals u squared plus 2as.
Yep, I put it here. All right, so yeah. So how fast is the stone going at 2 seconds?
Wait, oh. What's the question? What is its instantaneous
Instantaneous
velocity?
velocity and acceleration at the highest point. Okay.
Wait, I don't need to use the equations for this then, right?
For the first part, no, you don't have to. But the one I gave you, you
Um,
have to.
yeah. Okay, so the first one, it's a v equals 0
Uh-huh.
and a equals negative 9.81.
Correct. So again, I'll just put the source of what we're doing here. Because I don't want to be plagiarizing. So here's the source. There. All right, this is the last one we'll do, and then I guess we can still do one more for projectile motion, but I'll give that problem there, yeah, at the end.
Mm-hmm.
Okay.
Uh, which equation do we use for the second one?
This one, the how fast is the stone going, right? So again, you set up the table so you can see which ones are not given. You're given an initial positive velocity, you're given t, you're looking for how fast it's going, but you're also given something, right?
Mm-hmm.
So again, um, just organize the information into the table for you to see that. Suvat.
So use 30
For what?
for u.
U,
U is 30.
correct.
And
V,
we're looking for v.
yeah,
So
so question mark for
v
now.
equals u plus at.
Okay, so our A is, what's our A and what's our
Negative
T?
9.81.
Negative 9.81. Okay, let's use 9.81 now. And the time is 2 seconds. Yeah?
Yes.
Okay, so you're right. You're gonna have to use this. We're gonna have to use v squared equals u squared plus 2as.
I got 49.62.
Mm-hmm. So that's gonna be 900 minus 2 times 9.81 times t 2 s. Actually, no, sorry. We're not supposed to use the v squared equation. You're supposed to use the s equation, the second equation, right? There. So let me redo
Oh,
that.
really?
Yeah. It's gonna be easier because you're given time. Right? You have time. So again, time, acceleration, u, and v. So actually you need this one. Right? I'm getting a
Yeah, I
bit
did.
tired. Yeah, I'm getting a bit tired. I got lost there. Okay. So anyway, There, yeah. So we're gonna use that. We're gonna get V equals 30 plus negative 9.81 times 2. So that pretty much means 30, put this here again. So cancel that. 30 minus 2 times 9.81. It's gonna give us 10.38 meters per second. Okay. All right. Get this? I think you got the same answer. All right. Great. So last one. Oh, sorry. We've already extended quite a
Can you
bit.
go back again?
Yeah, sure. We've extended quite a
Uh,
bit already, CJ. So would you like to continue this next time then?
okay.
So we
Wait,
can.
when I did that, I got never mind. You put negative 9.1.
Yeah,
I put positive.
you have to put negative because you have to put into consideration the directions.
Mhm.
Going up, the V was going up, but A is going down, right? So
Yeah.
okay. All right. So we'll do projectile motion when we get back on Sunday, right?
Yes.
Okay. So we'll do that projectile motion. Again, same technique, but now with 2 dimensions. Okay. So all right. Any questions before we end here, CJ? Any questions?
No, I think that was good.
Okay, great. So we'll continue this again next week, next Sunday. I'll see you then. Right? Have a good evening.
Okay. Thank you. You too.
All right. Bye bye now. Okay. On so if there's anyone on the stream, that's it. Again, so the key idea here is what we did. We just made sure that everything is visually easy to see so that it's easier to solve. Okay. Whether we're doing SUVAT, kinematic equations, or resolving forces, in any case, whether it's the normal or the regular forces that we see, or whether it's a ramp problem, it's gonna be the same thing. Tables are not only really great at organizing data, tables are really great at organizing how you solve the problem. So keep that in mind when you do that. So thank you. So anyone who would be listening in later on or watching this later on, thank you for watching. Right. So before I go, don't forget, whatever platform you're doing or you're using, don't forget to like and subscribe or share. So we are on 5 platforms. I stream on 5 platforms, but right now I'm only active in YouTube, Facebook, and Twitch. I'm still setting up the Instagram and TikTok. So once that's ready, of course, you can join Instagram and TikTok. Okay. So for now, that's it for tonight. I will see you all next time. Till then, stay freaky, everyone. Bye bye now.